Hello students, in this video I am going to go over how to find the inverse of a function and why there is even a need, and first and foremost what exactly is an inverse. So before I answer that last question there about what is an inverse, let's take a look at a scenario. So right now on the screen you see there's an equation. C of f is equal to 5/9 f minus 32. This is a conversion equation, and what this is this is a conversion going from Celsius to from Fahrenheit to Celsius. What am I saying? This is C as a function of f, and what this means is, okay, F is the temperature in Fahrenheit, is the input. And C is the output. So whatever I throw in for F, in return, I'm going to get a temperature C in degrees Celsius. So for instance, if I wanted to figure out what is the temperature in 72 degrees Fahrenheit in Celsius, this is not saying 72 times C. This is saying wherever you see F in the equation C of F, you're going to replace it with 72. So you're going to get 5/9 times 72 minus 32 is equal to 5/9 times 40, or it's 200 over 9, or it's approximately 22.2 degrees Celsius. So let's say you are you're in a chemistry lab, okay, and all the experiments are conducted in the metric system, and so but you only have a temperature reading in Fahrenheit. So something like this would come in handy. Now suppose you wanted to travel outside the United States, and everywhere else in the world, okay, the temperature reading is in Celsius, pretty much, with the exception of some places. But most of the world, okay, uses degrees Celsius. And so what then? Well, what the situation is, we want the temperature input now to no longer be F, but to be in C. So we want C to be the input, and we want F to be the output. Why? Suppose you went to a foreign country and all the temperature reading was in Celsius, right? And you wanted to figure out, well, what exactly is 15 degrees Celsius? I don't know. There's no real perspective on things because you didn't grow up using degrees Celsius. So what would be the temperature reading in Celsius, 15 degrees Celsius in Fahrenheit? That'll give you a better sense of what the temperature is outside. So in that case then, if what we can do is we can then find the inverse. So what exactly is the inverse? The inverse is exactly what it sounds like. It's going the other direction. It's going in the opposite direction, right? When you hear the word inverse, you're flipping things. So the input and output are now reversed. So to find the inverse function, we're going to isolate the original input and turn it into an output. What do I mean by this? So in the original equation, okay, what we had was C is equal to 5/9 F minus 32, right? So now what we're going to do to find the inverse, okay, we're going to isolate F. So what we're going to do is we're going to take this equation and we're going to isolate F. So we're going to multiply both sides by 9/5. So I have 9/5 C is equal to F minus 32. I'm going to add 32 to both sides. So I have 9/5 C plus 32 is equal to F. Now, this equation, C is isolated, F is a function of C. So in other words, if I throw in some temperature reading in Celsius, I will get in return an output that is Fahrenheit. So going back to the question I posed maybe a minute ago, if the temperature reading outside was 15 degrees Celsius, what would that be in Fahrenheit? Well, that would be 9/5 times 15 plus 32. And the temperature reading outside in Fahrenheit is therefore going to be 27 plus 32, or it's going to be 59 degrees. So temperature reading of 15 degrees Celsius is 59 degrees Fahrenheit. Okay, so again, just to summarize, why is there an inverse function and why do we need it? An inverse function is needed because suppose sometimes we want to, reverse the situation where we want the output to become our input and we want the input to become our output. When will this ever become useful again, other than like just temperature conversion, you may ask? Well, let me give you a more pragmatic situation. So suppose I give you another scenario now. That's the beauty of math and science, right? It's super pragmatic and versatile. So let's say I have this equation here, and let's say this equation tells us the cooling effect of a body, okay? So this is the cooling of a body, okay? And where lowercase t is measured in hours and capital T is measured in degrees Celsius. So what this does, okay, the input in this case is lowercase t, as the equation here is suggesting. Capital T is the output. What is this equation telling us? This is saying that at any given moment in time, we can then figure out what the temperature is while it's cooling. Okay, so for instance, after 4 hours of a body cooling, we can then be able to figure out what is the temperature of that body. When I say the body, I don't mean like a human body. I just mean something. Okay. And by the way, this equation, this cooling equation, is not quite accurate. So, but I'm just using this for demonstration purposes. So, an actual cooling equation doesn't quite look like this. Okay. But again, I'm only using this for demonstration purposes. Okay. So after 4 hours, I want to find out what is the temperature. Okay. So I can then say, oh, T of 4, right, is equal to 10 plus 10 over 4 plus 1. That would give me 12, right? Because 10 over 5 is 2, and 10 plus 2 is 12. So this is saying after 4 hours, it would be 12 degrees Celsius. Well, what was it? After 1 hour of cooling? Well, that would be 10 plus 10 over 1 plus 1, and that would be 15, right? So that makes sense, right? After only 1 hour of cooling, the temperature reading was 15 degrees. After 4 hours of cooling, the temperature of some body is 12 degrees Celsius. That makes sense. Okay. Now, let's say, okay, you are you're a scientist, and you have a very similar body of a very similar makeup, okay? And now, okay, you're told what the temperature is, or not told, but you know what the temperature is, okay? So now the temperature is your input. So you know the temperature of the body, but you don't know. You have no idea how long that time, how much time has passed since it started to cool. So therefore, now your lowercase t is the output. So in this case, okay, this again, the situation has been reversed. The temperature reading, okay, originally was the output. Now we're making an input. So why would this be useful? Well, so let's say if this equation actually described the temperature cooling of an actual like organism that just deceased, right? Then the forensic scientist would then be able to compute, well, how much time has passed since that particular organism has passed, right? So you see do you see the application and the versatility there, right? So because of this, okay, we need to find the inverse function. So we need the inverse function. So we're going in reverse, okay? And the technique was, one more time, we want to isolate the independent variable from before. Whoops. We want to isolate the independent variable from before. So we're going to try to isolate t, lowercase t that is. So what are we going to do? So I'm going to replace, get it out of this function notation here and just write capital T, because that is what we're going to try to make lowercase t as a function of. And what we're going to do is we're going to subtract both sides by 10. So I get 10 over t plus 1. I then multiply both sides by t plus 1. So I get t minus 10 times t plus 1. My objective is to isolate lowercase t. Now, in order for me to do that, I need to get lowercase t outside of the parentheses and then bring everything else over. So what am I left to do? Well, what I'm going to do is I am going to distribute the quantity of t minus 10 into that set of parentheses there, giving me lowercase t, capital T minus 10, plus capital T minus 10 is equal to 10. I am going to subtract over this guy, giving me lowercase t times t minus 10 is equal to 10 minus capital T minus 10. Again, I'm being really strategic on how I am distributing, okay? Again, having no understanding my end goal here is to isolate t. My second to last step is to divide over capital T minus 10. So I have lowercase t is equal to this guy. And with just a little bit of simplification, yes, I can certainly reduce the numerator to try and combine like terms, okay? There are different ways that we can re-represent this. So I am going to distribute the negative, okay? So I end up with 20 minus capital T all over T minus 10. So this, as a result, okay, is going to be the equation that I was looking for. So in this case, okay, so let's say if the temperature of the body was now 5 degrees, okay, so, or actually, let's not make it 5 degrees. Let's make it 10 degrees. I'm sorry. Let's not make it 10 degrees. Let's make it 10.5 degrees, okay? I want to know what is the temperature, or how much time has passed before the body has cooled to 10.5 degrees Celsius. So in order for me to do this, I am going to, this is my input, and I want my output to be time. So my time now is going to be 20 minus 10.5 over 10.5 minus 10. What is the time then? Well, 20 minus 10.5, that's 9.5. 10.5 minus 10, that's 0.5. 9.5 divided by 0.5, that is a total of 19 hours. Okay, so in other words, 19 hours has passed for this particular body to cool down to 10.5 degrees Celsius. Okay? So again, to summarize, why do we need to have an inverse function? Well, an inverse function is needed because sometimes, given a function, we may need to go back and find things in reverse. So what was originally the input? We want that to be the output. And what was originally the output? We want that to be the input. That's where an inverse function comes in useful.